let's go ahead and get this class started. Today is the 1st of November. Yep. Time flies. Go. Alright, so alright, so we'll first deal with the nested call homework assignment, and then we'll talk about the next homework assignment. Okay, so the next homework assignment is kind of like the reverse of this one, where you have to write the subroutine. I'm the one who is calling. Okay, as opposed to the nested call, which is, I wrote the subroutine and you guys were the ones who do the calling. Okay? So we'll go through this one first, and then we'll talk about the next one. Okay. So this is the code that you're supposed to implement, which is a nested call. It is not recursion. So in this case, because we know that we have to push the second parameter first, which means the best way to do this is to perform this call first. When it returns register A, you put it on the stack. Okay? Then you perform the second call. Whatever this returns, you also push it on the stack. So at that point, you will have two things on the stack. One being the result of 6 minus 4. The second one being 5 minus 1 on the stack. Then you perform the third call, which also naturally puts the result into register A, and you're done. So it is easy to say, but in order to actually do it, there are a few things you have to take care of. So we'll go ahead and I'm going to go ahead and actually write this program and test it in Logisim, just so that you can see how the whole process is done. So let's go ahead and use mousepad. There we go. All right. So I'm just trying to figure out a way to display. Oh, that is good. This is fine. So I'm just going to display both the code that I'm supposed to implement and also the code that is doing the implementation on the side. All right, so the first thing we need to do is to implement calling the sub, which is subtract, with 4 and 6 as the parameters. Because we always push the second parameter first, this means I have to call. Okay, so before this, just to be safe, we initialize the stack pointer to be 0. So that when it rolls over after decrement, it becomes the highest possible location. And main is not really a label being used. It is just indicating this is the starting point of the code that is calling the subroutine. So to do this, we just load A with 4, decrement D to allocate a byte on the stack, and then we do an ST instruction to where D points to, and then we are going to store the value of A at the place where D points to. Okay. And you will see that we're going to use the same kind of sequence of instructions quite a few times. The second one is going to be a 6 because we are pushing the first parameter second. So are we doing okay so far? Pushing 4 first and then push 6, and then after that we push the return address. You will need 3 different return addresses in this case. So I'm going to have LDIA main return address 1. Load it into A, and I immediately write down the definition of the address of the label itself, so I don't forget. So once again, we have decrement D, ST, and then DA. And at this point, I have pushed the 2 parameters and also the return address on the stack. It is time to go to the subroutine, continue execution in the subroutine. When the subroutine is done, it's going to come back here. When it comes back here, I got 2 things to do. Okay, I can increment D. So these 2 increments are going to deallocate the parameters from the stack. And the return value of 6 minus 4 is stored in register A. But I kind of need to keep it around. It is my second parameter to the third call of sub. So the best way to do it is to push it on the stack at this point. So I'm going to say decrement D to reserve 1 byte on the stack, stda. So this is basically pushing the result of 6-4 on the stack, or 6 minus 4 on stack. Is that okay? Yep.
Is there a difference from just, do we have to increment and decrement, or can we just?
No, you can, because
then push?
Yeah, you can get rid of these two instructions together because they cancel out the effect of each other. So you can delete these two, but I prefer to show both because because the second increment serves a different purpose compared to the decrement. The increments are deallocating the parameters as opposed to the decrement is reserving the space for the second parameter to the last call of sub. So that's why conceptually I like to display the increment and the decrement, even though functionally speaking this is just wasting clock cycles.
Well, I'm making sure that we wouldn't have to always decrement every time to erase it and whatnot.
Right. You can do what we call Peephole Optimization in the compiler. This is called Peephole Optimization. The compiler in its code generation engine, it has certain rules that basically say, oh, if you see this stupid sequence of instructions, replace it with this smart one. Okay, so you can do that here. Yep. Okay, so now that we are done with this, I'm going to use a very bad approach, just copying and pasting. So we'll copy and paste again, and then this time we're dealing with the 5 one. So this one is a 5 1, this is a 5, and we need to change the address to 2. Okay, cannot use the same one. So at this point, after we deallocate both of the parameters, we have to push the result of the operation again, which means we decrement D 1 more time, and then we push register A on stack, which is basically just storing A to whatever D points to after the decrement. And now we can call it the third time. So to call it the third time, I am going to copy and paste again. So this time we're going to copy and paste this chunk of code over here. Instead of 2, we have 3. Yep, that's it. Are there any questions about the approach to this problem? Okay. What if yeah, go ahead.
I was gonna say, mine, as far as I can tell, does exactly what you did, but I was still having the same problem I had in the lab at my home after I tried loading the ROM and everything.
Okay.
So I'm really not sure why, because it goes back to line 0 and starts rewriting. Or just writes 20 there. I'm not sure what that.
So did you re-download the all.rom file?
Mm-hmm.
Okay, let me just check with the rest of the class and make sure that we are all consistently using the same file. So is the rest of the class using the last attached file in your simulator?
Yeah.
And it is not giving you any problem with this assignment at least?
No.
Okay. So I'm not really quite sure what is happening with your code, but that seems to be the issue. Did you re-copy the assembler? Because if the assembler generates the wrong kind of code, that can cause issues as well.
Did you update the assembler? Or?
I have not updated the assembler for a long time.
Okay.
But that's potentially, another reason. Okay. All right. So, but since I wrote this code, might as well test it first, right? So we'll go ahead and test this code. Copy and paste, and go to the assembler to assemble the program. And someone in my other class, in my Tuesday, Thursday class, wrote a command line assembler for this architecture. So I might share that with you guys once I double check and make sure that works. Go to cisp310, shared processor. It's probably on the first page, like the most recently used file. Okay. Go to source, paste. Make sure we don't have any errors. Okay, very good. And the rest of this code we can just kind of, oh, we can get rid of this, but then we have to copy and paste the other portion because the actual subroutine is not here. And that's why, you know, in the actual JMPI instruction, it says, you know, the label is not defined. So that's because I forgot to download this and copy and paste that code. So we'll do it here. And then we open it using mousepad. So we open sub. And we just need to copy and paste the last portion, which is the subroutine itself. So copy and paste. There we go. And the error, you know, goes away because the label is now actually defined. Then we go to the RAM file tab. Download as, and we'll just call this sub.csv. And now we can use the simulator to double check. So java-jar. Okay, I'm gonna do this. History, look for Java. Okay, 1994 would do the trick. There we go. It's a little nifty trick in Linux. Okay, reset the whole thing. Load the memory of RAM from sub.csv, and then we can just run the code. Control K, and when it's done, we go to the register bank. Look at register A. It has a value of 2. Okay, is that right? 6 minus 4 is 2. 5 minus 1 is 4. 4 minus 2 is 2. So I think we got it. All right. So are there any questions related to this homework assignment? Yep.
Can you just show the third section again?
The third section.
That's where I was missing.
You mean here?
Yeah, that's right. Okay.
You mean this part?
No, I was just the third section where you
Oh, okay, I see.
subtract the 2 that you had already subtracted. That's where it was.
Uh-huh.
Okay.
Okay. Yep. Okay. So in order to really understand this program, oh, okay. I'm just looking at, no, this is fine. This is the file that is included in your homework assignment. So this is fine. It has a single call to sub, and it is subtracting. This one subtracts 125 from 45. So that's why it ends up with a B0, which is a negative value. All right. Are we okay with this? All right, cool. So now we're moving on to the next homework assignment. So this one is going to be due in a week. I think you guys probably can get this done before, you know, the due date itself. So it's called divide again, subroutine. So this is a subroutine. So in this particular homework assignment, I want you to implement the code of divide, but this time as a subroutine. As a subroutine, so you can download this file, which is really simple. It gives you the prototype in C so that you understand what the interface is supposed to look like. So I'm going to save this one into the file here so that I can just open it with Notepad. So here's Notepad, open this one as, oh, what is the name?
It's at the very top.
Yep, div sub.c. Thank you. So this is the prototype. I want this particular subroutine to call div, div, so you have to use that particular name because my code is going to test it based on that assumption. It's going to take 3 parameters. The first parameter is a 8-bit unsigned dividend. The second one is an 8-bit unsigned divisor. The last one is a pointer. The last one is a pointer to a byte. if it is non-null, if p remainder is not null, then you want to store the remainder where it points to. If p remainder is null, then you just ignore it. Go like, okay, we're just tossing the remainder away. Okay. The actual return value of div is the quotient. So the quotient is always computed and always returned as the return value, but the remainder is only going to be stored if the pointer p remainder is not null. Is that okay? And by the way, null is just 0. Okay, so test whether p remainder is 0 or not. If it is 0, it is null. If it is not, then it is not null. So do we know what to do with this particular subroutine? So you can kind of reuse your code, okay, from the previous homework assignment. You can use successive subtraction, okay, because the other way is uses up all the registers, or close to all the registers. So it's not a very viable way of doing this. So you might want to just reuse the successive subtraction method to do division. So the key now is not the division code itself. The key now is how do you get the parameters into the registers that you need to do the computation. When you're done, how do you return the return value, which is the quotient, and how do you check p remainder so that you can store the remainder when I specify a location to store the remainder. So those become the actual issues. I can even give you the entire pseudocode for this entire subroutine in case you might find it useful. I don't think it's going to be useful, but just in case. So the code to do this is really just like what you had before, which is while, okay, divisor, we need a quotient. So you need something to keep track of the quotient. I would use a local variable here, uint at quotient, and then quotient is initialized to 0, which is important. And then the rest of this is really just while dividend is greater than or equal to divisor. And then in this code, you first increment quotient, and the second thing you do is you say dividend minus equal to, basically subtracting divisor from the dividend. So the question now is, what do you do after this? Okay, so what you do after this is you say if p remainder. So we are not checking what it points to. We are just checking the pointer itself to see whether the pointer itself is non-zero. If the pointer is non-zero, we want to store the remainder, which is currently in the dividend, into where it points to. And then the return value of the entire thing is quotient itself. So that's basically the C implementation of what I'm asking for. The first portion, which is here, is something that you already have. And if you don't like your own solution, you can use my solution to that homework assignment. That's not a problem. So the big question now is, how do you get dividend into the register? How do you get divisor into that particular register? When you're all done, okay, how do you check whether the parameter p remainder is null or not? And if it is not null, how do you store the dividend, which is now the actual remainder, into the place that p remainder is pointing to? And how do you return quotient as a value? So those become the actual questions of this homework assignment. Are there any questions about this one? Yes? No? Is okay? All right. All right. Yep, go ahead.
Following the same conventions as the other divide one, where the same registers are going to be the divisor and the dividend? Like,
you can, I mean,
so
you can.
Or does it just matter the end result we get?
So in this case, you have to make sure that you follow the convention that register A specifies the return value.
Okay.
Okay, so let me get back to the homework assignment description, because it also outlines what type of convention is specified here. So this is the same stuff that we have been talking about. There's nothing really new in this convention list. Parameters are pushed in reverse order. Last parameter is pushed first with the highest address on stack. So that's already demonstrated by my solution to the subtract homework assignment. The second one is the return address is pushed last before execution continues in the called subroutine. Once again, that's also consistent with the subtract homework assignment, right? The called subroutine is responsible to deallocate storage used by the return address. So when you look at how sub is implemented, okay, let's go back to sub here. So when you look at how sub is implemented, you can see how once I put the return address into a register, I increment the stack pointer to basically deallocate that location from the stack. So that is what I meant when I said the called subroutine or the callee is responsible to deallocate storage used by the return address. Scalar values or scalar return values are stored in register A. Scalar basically means it is an integer, it's a pointer, that sort of thing. And in this particular program, it is definitely an integer. Okay, so register A should store the return value. The caller is responsible to deallocate storage used by parameters. So you don't have to worry about, oh, okay, I can use the parameters, but who's going to clean that up? I'm going to clean that up. The stack pointer should be right above the return address on stack when the caller resumes execution, because the return address itself is deallocated by the callee as the very last operation. So is that helping?
Okay, thank you.
Sure. So for this particular program, you are guaranteed that the divisor is not 0. So I won't give you a division by 0 type of problem. You can reuse portions of code from the earlier divide assignment. You can use my solution if you want to. You can use your own solution. Either way is fine. Turn in a text file with your implementation of the subroutine. There's no need to include any caller code that you probably will need for testing purposes. Because you need to set up, kind of like a test caller to make sure that your code is working. So you can, if you include it in the text file, it's okay. I'm just going to cut it out. If you don't include that, then just the subroutine itself, that's best. So are we okay so far? Yep.
Are we assuming again it's always unsigned numbers?
Yes. Because the C code is definitely giving you the type of the parameter as well as the return value as unsigned. Is that okay? Is anyone planning to do this recursively? Hey, anything that is done in a loop can be done recursively. Yep.
No, it's probably was.
Okay. Is that okay? All right. Well, if this is out of the way, we can look into more subroutines. I can give you more examples of how to write subroutines and how to call subroutines in assembly. Is that okay? All right. Okay. So we'll start a new subroutine, and I'm thinking about more string functions. Okay, string copy this time. So we are looking at string copy. So the first thing we want to do is to look at the documentation of string copy, which is starting with a big no-no. Okay, if you just look at string copy, strcpy, you will find out that string copy it doesn't say in bold that it should not be used. I am surprised.
I saw somewhere saying it was inefficient.
It's not a matter of efficiency, it is a matter of buffer overruns, right there. So beware of buffer overruns. But I thought it would be even more prominent as a warning, like in bold and flashing, say do not use string copy. This is a little disappointing. Okay, but it's okay, since we're just using it as an example. So this is the subroutine string copy. It has two parameters. The first one is the destination. The second one is the source, which is consistent with the opcode that we use in this class. When you have CPR AB, A is the destination, B is the source. So it's kind of consistent with that convention. It also returns a character pointer, which turns out to be the destination itself. So whatever dest is the return value of this entire subroutine. So when you look at the function or the description of the function, it copies the string pointed to by source, including terminating null byte to the buffer or to the destination pointed to by the dest or the destination. The strings may not overlap, okay? In other words, because if the strings overlap, you may encounter a situation where the copying cannot stop, because the copying is going to overwrite the original terminator from the source. So that's why, when they overlap, you can have, very, very bad behavior of your program. And the destination string dest must be large enough to receive the copy. There's no way string copy itself can enforce this, which means the caller is now responsible. The destination has enough space to receive the copy. Okay. A simple implementation of string and copy looks like this, which means string copy is a little bit easier because you don't have to count n. The return value is really just a pointer to the destination dest. Is that okay? So how do we do this? Do you guys want to do this recursively or iteratively?
Recursively.
Recursively first. Okay, let's do it recursively first. Okay. So char str cpy, and this is char dest, const char source. And I think the original definition also has const. I can be wrong. Let me double check. Yep, source is const char, because we don't want to change what the source is pointing to, only what the destination is pointing to. So that makes sense. Okay, there we go. All right. So with any type of recursive algorithm, the first thing you think of is, when do I stop? In other words, you're trying to be as lazy as possible. When do I have to do the least amount of work or nothing to do, right? So we'll check that first. And the easiest thing you can say is, oh, if the source is pointing to a null terminator, it's easy for me. Does that make any sense? The source is an empty string. Woohoo! Cool. So that means I can use an empty string too. So empty string is just saying dest is source, because I want to copy that null terminator. Does that make any sense? I see a null terminator character in the source. I'm going to copy it because I now become an empty string as well. I'm all done. Cool. Else, okay, what do we do? Well, the else is really corresponding to the fact that source is pointing to a non-null character, which means, okay, I guess the first thing I can do is to make that copy, which also means this part can be factored out of the conditional statement, but we'll do that later. But the string is not ending yet because the source is not pointing to a null terminator. So this is a good time to call string copy again. And we say string copy. And this time we can ignore the destination, because the destination is going to be 1 byte beyond the 1 byte that I just overwrote. The source is also 1 byte beyond the byte that I just copied. So that's how it's going to call itself recursively. And then we just say return dest here. We are done. Yep.
So we could just have an if statement. If it is reading something, just do string copy and put the destination equals out.
Yep, exactly. So that's what I'm going to do here. We factor out this part because it has to be done in both cases. So now our conditional statement has no then portion, which means I can now flip the polarity of the condition and get rid of this section here. So that's the quote-unquote more simplified version of it. Are we doing okay so far with this code? Do you guys like recursion? It is a different way of looking at things. Okay, I'll just kind of put it that way. It's just a different way of looking at things. You're looking at a bigger problem, and you say, okay, what is the trivial case that I can solve right away? And then you ask the other question, which is, what if it's not the trivial case? How do I break the big problem into a smaller problem that I can solve immediately, and a sub-problem that has the very same nature as the problem that was given to me in the first place? That is how you think about recursion. All right, so let's go ahead and implement this as a recursive subroutine. Okay. So to do this, I'm going to comment out every single line. There we go. All right, so we put a label here. Okay, this is the entry point of the entire subroutine, and it is always a good idea to point out what is on the stack. So we got source on the stack, we got destination on the stack, we got the return address on the stack. Okay, so that's the condition of the stack at the entry point of this entire subroutine. Okay, so it seems to me that we need to retrieve source and destination, and also you figure out what source is pointing to, figure out what destination is, and then change destination to whatever source is pointing to. Okay, so we do the usual trick. We use register C as a copy of register D because we don't want to mess around with register D. And then we kind of just do the rest, which is figuring out where source is. So we have the increment C. Okay, so if I were to comment what C is pointing to, so right now C is the address of the return address. When I increment, it becomes the address of the destination. It is not destination itself, it is the address of the parameter destination. So I have to increment it one more time so that it is finally the address of source. Once C is the address of source, I use the LD instruction so that A is actually source now. So A is the parameter source. But the parameter source is a pointer itself, and what I want to do here is to dereference it. So I'm going to do another LDAA. This time A is whatever source is pointing to. So the right-hand side is done. Now we move on to the left-hand side, which is to compute, okay, what is this? What is it pointing to? So to do that, I'm decrementing C, because C is still pointing to source. Decrementing C means it is now pointing to destination. And then we do an LD instruction. I cannot use A anymore because A is used here. So we're going to use B. So now B is the parameter destination itself. We know A has the byte that I want to store. It is the right-hand side. And B points to the location where I want to store that byte. So at this point, a single SDBA will do the trick. Because now we are basically saying dereference B, which is dereferencing the destination, and store into it whatever the source is pointing to, because that is now in register A. So to be more exact, this chunk of code should go here, because this chunk of code is implementing asterisk or dereference destination equals dereference source. So are we doing okay so far with this? Kind of, okay. So then the next thing we do is to say, oh, okay, we still need to rely on source because we need to do this conditional statement. So at this point, fortunately and very conveniently, we still have this, whatever source is pointing to is still in register A, which means we don't have to go through all that stuff just to figure out what source is pointing to. And we want to compare it to a 0, because when we use statements or conditions like this, what we're really asking is that non-zero? Okay, so this part is optional. If you miss this part, it's okay in C because it is automatically implying that non-zero is true. Okay, you cannot do this in Java. How many of you program in Java? Okay, you cannot do this in Java because Java says source. Well, okay, first of all, Java has no pointers. Okay, so even if you have a character already, you still cannot use a character where a Boolean is expected, because Java has has tighter type checking. It does not automatically convert non-Boolean types to Boolean like C does. But this is C, we can definitely do it like this, but this makes it easier to spell out the assembly code. So in this case, we basically put a 0 into B, so the B is 0. We can do the compare. This compare, you can do it, compare AB or BA, doesn't really matter, because we just want to know, is it 0 or not? Okay, if it is 0, then we branch around to the end. So we go to end if, the label, and the end if label is going to be here. If we do not, then we are going to call the subroutine recursively. So to call the subroutine recursively, we kind of have to go through all this trouble again, okay? Except at this point, C is pointing to the destination. We wanted to point back to source first. So at this point, I'm just going to comment and say that C is still pointing to destination last time we checked, right? So we can save a few instructions by making that assumption. So we want to increment C so that C is now the address of source. We do an LD instruction so that A is actually source. We increment A so that A is now source plus 1. Then we push it on the stack. Decrement D, ST, D, A. Push source plus 1. What are we pushing? Are we pushing a character, or are we pushing the address of a character? Address of a character. Very good. Okay. All right. So this is done. Let's move on to destination. So according to this map here, destination is 1 byte below source, which means we decrement C again. C is now the address of destination. And then we do about the same trick. Okay, LDA C. So the A is now destination. Increment A. So the A is now destination plus 1. We decrement D to allocate 1 byte on the stack, and then we STDA so that we are basically pushing destination plus 1 on stack. So at this point, we have the second parameter push on the stack. We have the first parameter push on the stack. It is now time to call the subroutine. So to call the subroutine, we are going to do an LDIA with a string copy return address, which I define here. And then we do the usual thing, decrement D to reserve that 1 byte for the return address. And then we store the return address to what the stack pointer points to. So we are basically just pushing stdcpy return address. And then don't forget to do the actual jump, because this doesn't do a single thing unless you do a unconditional branch back to string copy. When string copy returns, when the recursion returns, then we have to say, okay, it's time to clean up the stack. So we have to increment D twice to clean up the stack. And that concludes this particular call. So we are done here. When we are done here, we now need to do the return destination. So this is the really, really tricky part, because people might think and say, let's check let's check C, register C. Last time we checked, register C is pointing to the destination. So why don't we do this, right? Why don't we just say LDA from whatever C is pointing to, because now A really should be the destination, and then we can just go through the usual code of returning, which is LDBD. And then increment D, and then we do a JMPB, and we're all done. The problem is, this is an invalid assumption. Why is it an invalid assumption? You do a recursive call, right? You do a recursive call after we make the note that C is the address of destination. So why would this not be such a good idea? What is the first thing that the recursive call is going to do? Okay, the recursive call is calling string copy, which means the very first instruction it's going to do is this. And what is that going to do to the assumption that we were just making? When you call a subroutine, you can no longer count on the registers A, B, or C to retain its current values. Okay, so that's why I said, hey, this looks convenient, but we cannot make that assumption anymore. Because when the subroutine returns at this point, register C can be changed by the subroutine. And in this case, we know for sure it is going to change register C. Okay, well, I guess we cannot do this conveniently. So if we're not going to do this conveniently, we just have to do it the longer way. CPR CD again. Because register D is still our stack pointer. And the stack, assuming our subroutine doesn't mess up the stack, our stack pointer will still be pointing to the same place, which is the return address. The destination is 1 byte on top of that. So now we say increment C. So if I were to comment this, this is basically saying C is the address of the return address. When I increment, after I increment, C is now the address of destination, which means, we're pretty close to what we need. So we just say LDA C. So this A is now the actual destination, which is our return value. And then the rest is just the usual return code. Is that okay? So this is the recursive way of doing string copy. I'm only illustrating it to show that it is possible. It's not a good idea. Why is this not a good idea? I mean, it's possible. It's just not a good idea. Yep.
Is it because the stack is small?
Well, our stack is extremely small. That is true. So it's also very wasteful. Okay. So if you're looking at a 64-bit architecture, the return address itself is 64-bit. Okay. The parameters each is 64-bit. So we are looking at 64-bit for destination, 64-bit for the source, 64-bit for the return address for each level of invocation. And we have one level of invocation for each byte that we are copying. So if you're copying 512 bytes, you're guaranteed to consume 512 times 64-bit on the stack. At least that much. Okay, there'll be some extra stuff too. And it's also very slow, because every time you do a recursion, guess what? You have to access memory. You have to access the stack. You have to push the return address on the stack. Every time you return, you have to pop that return address from the stack. The stack lives in RAM. Everything that you do with RAM is slow. Things that you do purely using registers are fast. Okay? So that's why the recursive way of doing this is actually extremely slow compared to the non-recursive way. But I'm only doing this because I want to show you how to do it recursively. Because now we can see it from the perspective of the callee as well as the perspective of the caller in a self-contained package. So that's the reason why I'm doing this in the recursive way. Okay, so I claim that this is the answer. Well, you would say, but I'm not sure. Show it to me that this is correct. So we'll complete this program, and we'll do an LDI source. Okay. Source string. I cannot use source again because in assembly language programming, especially in this assembler, there's no scoping ability. So all labels are global throughout the entire thing. So I have to be careful with this. So we'll load A with source string. We'll push it on the stack, and then we'll do the destination, or we'll call the buffer. Okay, decrement D, stda, and then we'll have the return address, main return address, and main return address is here. Decrement D, allocate a byte on stack, store the return address on the stack, and then we call the subroutine itself, called string copy. And when we come back, always remember to deallocate the space used up by the parameters, and then we can now have a hold instruction here. So now it is just a matter of allocating for the source. Okay. So the source string is going to be, I can spell my name again. Okay, so we'll go here. ASCII. You don't have to read this. I know the characters are very small on the projector. So I'm just looking up my T, the ASCII code of uppercase T. It is 84. Okay, 84. And then we have lowercase a, which is 97. And then we have lowercase t, which is A, B, C, D, E, F, G, H, I, J, K. So that's plus 11. 96 plus 11 is 107, I think. Does that sound about right? Yeah, close enough. Don't forget the null terminator, because we definitely need to make sure that it terminates with a null. And now we have the destination string, or the buffer. Okay, it's not a destination string, it's buffer. So even though the actual content of buffer really doesn't matter because it's not supposed to be initialized, the assembler that we have doesn't have the ability to allocate just say okay, allocate 6 bytes or whatever. So I really need to use a byte 0 or byte whatever. Okay, it doesn't matter what you use as this part of the expression, but we need these to say reserve 6 bytes. That's what I'm doing here. Is that okay? So I think I got the entire program done. Control A, Control C, go back to the assembler, which is here. Go back to source, and we'll erase the entire previous program and paste here. Make sure there are no errors. Okay, it's all good. Go to RAM file, download, and we'll download it as string copy. Switch to the simulator. Control R, reset everything, and then reload the program from RAM into RAM. This is string copy. And if I'm confident this is going to work, I would just do a Control K. If not, I'm going to go through all those things to track down what is happening on the stack. Okay, so let's say I'm not confident about the behavior of this program. I want to track down everything. How many bytes should I track on the stack? In other words, in theory, how many bytes should I be consuming in this case on the stack? We're doing string copy recursively. Okay, the string that we are copying is T, A, K, and then the null character, right? So the first invocation would have source pointing at the beginning of the entire string. The second invocation would have source pointing to lowercase a, lowercase k, and the last invocation is going to have source pointing to the null character because that's when we stop the recursion. So we have 4 invocations of string copy, and each one is going to consume 3 bytes, not 2, but 3 bytes, because we have the destination, the source, destination, and the return address. So each time we call, it will consume exactly 3 bytes. So we're looking at 12 bytes here. We're consuming up to 12 bytes on the stack, which means I should track 13 just to make sure that I'm not using more than I should with this particular algorithm. I should track program counter just so that I can look at the code and go like, okay, where am I here? Where am I here? Where am I here? I should track at least register D because that's a stack pointer. Because I want to know, if I do mess up, where do I mess up, and why is the stack pointer lower or higher than what it should be? So those are the minimal things to track if I'm not confident that this program will work correctly. Okay? But I'm optimistic. I'm not confident, but I'm optimistic. There's a slight difference between those two. Yep.
If we did iteration, we would only be using 3 bytes total.
Say again?
If we only did iteration, we would be using 3 bytes instead of.
Yes. So one iteration would use up 3 bytes. Yep. Okay, Control K, and looks like we're done here. All right, so we'll double check this program. Several things we need to check. First thing, we go back to the program, and because we know the destination or register A should end up with buffer, and that should be 17 in hexadecimal. So that's the first thing we check is whether register A has a value of 17 because it's supposed to return destination as the return value. So we go into the registers, and it is in fact 17. So that's kind of encouraging. Okay, cool. Then we look into buffer, which is in memory. We need to go to location 17. Location 17 should have the same value as location 13. So 13, 17 should have the same value. 14 and 18 should have the same value. 15 and 9, I think. 8. No, 9 should have the same value. So, but we should see those 3 characters repeating. So now we go back to the simulator, go to the RAM, and we have to use edit content because otherwise it doesn't. Well, I guess it's here too. You can actually see it. But we will go to location 17. This is 17. So 17 is right here, and it is repeating T. This is T, A. This is A. This is K. The null byte, we don't know whether it was copied here or not. So if you want to confirm that the null byte is in fact copied, what you want to do is to change your program, which is probably a good idea. I did not think of this earlier. You might want to initialize these to non-zeros, just to make sure that the null terminator itself is copied. Because otherwise, you might be masking a problem where the null byte or the terminating byte is not actually copied. That will be a problem. Is that okay? Shall we look at a non-recursive version of the same subroutine? Okay. So the non-recursive version of the same thing, we'll do it in C first, at least in theory, and then we'll do it in assembly. So once again, we have char pointer string copy, char pointer destination, const char pointer source. Okay, so how do we do this? This might do. While destination plus plus equals to source plus plus semicolon. I just need to store the original destination, so we'll say this is the original destination is destination. Return destination. Oh, return original destination. There we go. Because destination is changed by the loop. I think that should do it. Now, this is C code that will probably compile. Doesn't mean it is recommended, because I'm using an assignment operator inside a condition, which means the compiler would most likely give you a warning for this, because the compiler will say, don't you mean equal equal, because it is inside a condition, and most people want to use condition equal equal instead of assignment inside inside the condition. Do you see what I mean by this? This one here, the compiler might give you a warning about this. All right, well, since most of you seem like, it seems to me that you are not believing that the compiler would complain about this, let's go ahead and save it and then see what the compiler has to say. This is string copy.c, and I think I put it into the temp folder. Let's switch to the temp folder. Oh, we are already there. And it's string copy, okay. So we do a gcc-c, which only compiles, but it doesn't try to link it. Doesn't give us any problem. That's because I forgot to ask it to complain. Okay, so once again, when you configure code blocks, okay, especially any type of IDE, you might want to double check and make sure that you turn on all the warnings. Because in this case, if I did not turn on all the warnings, which is what wall is for, it doesn't say anything. But if I say wall, it says on that particular line, on line 4, it says it suggest parentheses around assignment used as truth value. In other words, if my original intention is really just comparison, I would have looked at this and go like, I didn't specify any assignment. I meant comparison. Why would it say anything about assignment? Ooh, okay. I forgot another equal in the equal equal. How many people have made that mistake in CISP 360? Many times. Did you guys need to turn on the warning so the compiler warned you about it? That saved you some time, right? Because otherwise, your program may actually work for a while before it breaks. This is one of those problems, that is very common in C and C++ programming. Okay, but this time I'm pretty sure this is what I want to do. So this code is actually a little bit hard to translate into C++, translate into assembly, because I'm using things that are really handy in C, but not as easy when you want to translate that into assembly. So if you want to make it so that it's easy to translate into assembly, don't do this, okay? Do not rely on side effects like that. Instead, you just say that as long as we are not pointing to, as long as I'm not copying a null character, then we do a increment here. And then when we get out of the loop, we have one more assignment here to make sure that this is not needed. I think we're good. There we go. So this code is a little bit easier to translate into assembly because I'm not relying on the side effect of a post increment, which works okay. It's just not as easy to specify in assembly language. Is that okay? All right. So we'll go ahead and implement this in assembly code. Okay. So we comment out every single line in C, and then we'll replace all those lines in assembly code. String copy, colon. Okay. This is the interesting part. We have a local variable. So if you have a local variable, you can kind of initialize and allocate the storage and initialize it at the same time by pushing destination on the stack. Okay, so I'm going to do that trick here. So what we do is we do a CPR, okay, just like before, CD. Okay, and if I comment, what C has at this point, C has the address of the return address, which is not what I want. Increment C, so that C now is the address of destination. That's what we want. So now we do a LD A from C, so the C is actually destination itself, and this is what I want to remember from the original destination. So now we do a decrement D, and then we do a STDA. In other words, we're pushing destination on the stack. This is my local variable original destination. So what is important now is to look at the stack again and figure out what is on the stack right now. What's on the stack is going to be source, which is pushed by the caller, destination, which is also called by the caller, which is pushed by the caller. Return address, once again, pushed by the caller, no problem. But D is pointing not to the return address because it is now pointing to original destination, which is something that I just pushed on the stack. So that's important because you have to remember every time you push something, you're changing the offset from the stack pointer to other items on the stack. So unless you keep a register like C to point to a particular fixed point on the stack and keep track of that, you have to basically recompute the address of other items on the stack based on what the stack pointer itself is pointing to. Okay. This is rather inconvenient, but it is the way it is. So we'll have a while begin here, and at the end of the loop, we know that we have an unconditional branch to while begin. So this part we know has to be done anyway, so we'll put it here. So after while begin, we want to do the copying, and then we check whether one or the other one is a null value or not. So now we can say, okay, C is still pointing to destination, and we want to grab source first. Source is 1 byte on top of destination. So it's probably a good idea to do this because when you're in a loop, especially, you may not want to rely on a specific register to be at a certain point on the stack. So we'll just copy everything here. But this time we have to remember C is no longer the address of the return address because we just pushed something else on the stack. So it is actually the address of the original destination. So increment C, oops, means C is now the address of the return address. Increment it one more time. C is finally the address of the destination. There we go. Is that okay? Okay. We want source, so we have to increment it one more time. So C is now finally the address of the source. We do an LD. So that A is source, and we need to dereference it. So we use another LDA, so A is now whatever source points to. That is my right-hand side of the assignment. Now I need to work on the left-hand side of the assignment. Decrement C, so the C is now the address of destination. LDBC, so the B is the destination itself, and now we can store into whatever B points to, dereferencing destination basically, whatever we have in A, which is the entire right hand side. So this part is doing dereference D destination equals to dereference source. Are we doing okay so far with this? Okay. So that is almost done, but not entirely, because we also have to check whether A is null or not. If A is null, it's time to exit the loop. So now we have to compare A to null, which means I can trash B now. B is now not really useful, so we can trash B. We can just say LDI B with 0, and then we have a CMP AB. If A is 0, which means we just copy a null byte, it's time to get out of the loop. So we have a JZI to while end, and then we specify while end here. Is that okay? Sort of? Okay. Once we get into the loop, we can now say, okay, C is still the address of the destination, so we can use it. Okay, it's still handy to do it here. So we want to increment destination, which means we have to do so we might want to make a point here. C is still the address of destination, so we use a LDAC, so the register A is destination. Increment A, so that A is destination plus 1, and then we do a STCA, so the destination is destination plus 1, and then we do the same thing with source. Source is 1 byte on top of destination, so when we increment C, then C is now the address of source. Do we do LDAC? So the A is source. Increment A, so the A is source plus 1. STCA, so that we have source equals to source plus 1. And then we do the unconditional branch back to the beginning, do another copy of byte, and check whether it's 0 or not. When it's all done, we have to go here to return the original destination. The original destination, guess what? Is pointed to by the stack pointer. So that comes in pretty handy. So, but we might want to make a note here. D is the address of original destination. So that comes in pretty handy, because all we have to do is to say, just do LDA dereference D. So that A, we just specify the return value, is in fact the original destination. And from here, we say increment D, so that we deallocate local variable original destination. And then we do LDBD, so the B is the return address. And then increment D, and then JMPB. That should be it. I mean, I am not going to listen to my own lecture, for sure. Unless I have insomnia or some problem with sleeping. And I was in the loop. Huh?
Do you put yourself to sleep?
Oh, I would definitely put myself to sleep if I were to listen to myself like this. But this is how I write programs. Basically, I'm spelling out what's going on my mind, what I'm tracking as I wrote the entire program. So I spell it out, but I also wrote the comment on the right-hand side of each line to basically say, okay, at this point, which register has what in it. Okay, so that is important, because it is important for you guys to understand, oh, why does register C has the address of the parameter source on a particular line after that line executes, like this one here. So you do have to understand that part. You have to understand how the stack is being used by the subroutine. Okay. All right. So this is my claim. This is the code that works. Okay. So we'll do some copy and pasting here. So we'll say new again, and then this time we have copy, paste. And then we'll reuse the first part of the program that we had earlier, which is this one here. So we'll reuse this part because it should have the same effect, even though string copy is now non-recursive. There we go. So now we have a new program to test. Control A, Control C, go back to the browser, go back to source. And the first thing we do is we're just going to paste it and compare the length of the two programs and see which one is longer. Well, we could do it in some other way too. So this is paste. We make sure that there are no errors. Okay. So this program turns out to be actually longer. The non-recursive version is actually longer than the recursive version. We can now go to the RAM file. Download. And I'll download it as a different file. So we'll call this strcpy1, just so that we can also look at the CSV file later on and compare the length of the two. And we'll close this window, go back here, and go back to main. Oh, it's already in main. Control R to reset everything, including the clock itself. load image, and this is string copy 1.cpy csv, and then we'll run it and stop. Check register A first. Well, first of all, we check the program, go to source debug, and the destination, which is buffer, is at location 17, just like last time, because main itself doesn't change. So we want to make sure that in the simulator, register A also has a value of 17. And indeed, it has 17. Cool. Now we look into the RAM content and make sure that the 17, at location 17, we have TAK also. We did actually copy the whole thing. And you can see it's there already. This is location 17, and that's the same as location 13. And then this is T, this is A, this is K, and this is the null byte after the K. So the non-recursive version of string copy worked as well. I just double checked it. So are there any questions? In other words, when you're writing code in assembly, there's a lot of stuff that you have to track. It's very tedious because you only got 4 registers to play with. Okay? You also have to keep track of where register C is pointing to, because register C is floating around. It's just going to like, okay, I'm pointing to this parameter now, I'm pointing to this parameter now. Oh, wait, we're going to go back and point to the local variable and so on. Because every time you access a parameter or a local variable, you have to start with the stack pointer. Unless you make a copy of the stack pointer at some point, then you can use that as a reference point. But the rest of the code, is kind of more or less straightforward. It's just very tedious. So do we have any questions about this part? Any questions? We've got about 5 minutes. So what I'm going to ask is something like this. If you are given the binary code of a program, like this, okay? Do you think you can automate not you, okay, but do you think a team of software engineers, a company, can automate the whole process and try to identify places where problems can occur? Like, there's a chance that this code may cause a stack overflow type of issue.
Wouldn't you also need the ROM file? Wouldn't you also need the ROM?
The ROM file?
Yeah.
Well, let's say you know what architecture you're dealing with.
Okay.
Now, the toy architecture is strictly used just in this class. I mean, you won't see the toy processor again after you're done with this class. So we're talking about the i386 instruction set for 32-bit. We're talking about the AMD64 instruction set for the AMD 64-bit instruction set.
So we're assuming that the team is familiar with.
Right. So we are assuming that you are given the specification of the instruction set and the opcode of whatever processor architecture you're dealing with. Okay. So the question is, can we look at the actual opcode, the program, the executable, and identify, hey, this part of the program can potentially cause a stack overflow, this part can potentially cause a stack overflow.
Sure.
So the first thing you do, okay, absolutely. So the first thing you do is you turn this code, which is all in machine code, opcode, which is really hard for us to read. You turn it back into, where's my notepad? Right here. So you turn it back into this form. That's an easy process. Okay, it's an easy process because when you look at an opcode, you just look up a table and say, okay, which family of opcodes have this particular bit pattern? Okay, it's the add family. Okay, within the add family, you have like 16 variants because you have 4 registers they can specify as the source register and 4 registers they can specify as the destination register. So you have 16 variants. But from the bit pattern, it's not difficult at all for a computer program to figure out exactly which add instruction you're dealing with, right? So you can now look at this code and say, okay, we can see with the AMD 64 architecture, the stack pointer is special purposed. In other words, they have special instructions like push, pop, call and return that only make use of the stack pointer. Okay? And you can now track and say, okay, how is the stack pointer used? And then you can track throughout the execution of the code and see whether it is dereferenced. And if it is dereferenced at one point, or a copy of the stack pointer is actually dereferenced, you look and see whether the pointer itself is altered in a loop. If the pointer is altered in a loop, and it is altered in an incrementing way, then you check the condition of the loop. Are we exiting because of a length delimited type of condition, or are we exiting only because we have just copied the null character? If it is just because we have copied the null character, something that is not length delimited, that means the loop can exit after it has overwritten content on the stack. Then we have an issue. Okay? So if this all can be automated, okay, so think about this whole thing, okay? It's definitely possible. Everything that we can do, especially when it's something that is rational, something that's logical, is analytical, we can probably code it with a program. So let's say a particular company has this program that can analyze, the machine code of some executable and look for Stack Overflow vulnerabilities. Okay? How is someone going to make money out of this program? This is a program that can automatically find Stack Overflow vulnerabilities of other programs. If you are a white hat, then you can say, okay, give me the executable, I will find potential flaws of your program, so that you can take it back to your programmers and say, hey guys, we have a problem here. Okay, you guys really should not be terminating this loop based on a terminating condition. You should be length delimiting when to terminate the loop. That's what a white hat company would do. On the other hand, if it's a black hat company, which means they're hackers or crackers, they try to do things to infiltrate other programs and stuff like that. They would use this program to analyze, important programs like SSH, the SSH client program and whatnot, and see whether there are ways to convince the program to get to a part that they should not get to. Is that making any sense?
Like using the overflow, like taking advantage of the overflow?
Yeah, exactly. So once you have a program that can identify and say, oh, this program potentially has a Stack Overflow vulnerability, you just save a lot of time from the perspective of a hacker, because all of these steps that can be automated is done automatically. Now, exactly can we exploit it? Okay, just because your program will crash doesn't mean you can exploit it. But once you know it will crash, there's a pretty good chance that you might be able to format the input or whatever is presented to the program to exploit that vulnerability. In other words, this tool can still save a lot of time from the perspective of the person who wants to find out, does this program have a problem? And I think that market is wide open, both in terms of white hat and black hat. I think that tells you something about the future careers that you might want to consider. Any questions about that? No questions? Okay. We got 1 minute to go. In the previous class, okay, you were there in CISP 440. I was just talking about how automation and AI are displacing jobs. Amazon is displacing 15,000 retail jobs every year at an increasing rate.
They're also hiring a whole bunch of people.
But not as much.
Yeah.
Not as many. They might be hiring 5,000 people for every 15,000 people that they displace. Okay, taxi drivers are getting displaced because once we have fully autonomous vehicles, we don't need taxi drivers anymore. Taxis will be fully automated. So you're now replacing, potentially hundreds, if not thousands, of taxi drivers in San Francisco with only about 10, 20, maybe 200 people who maintain all those autonomous Priuses or Prii. right? True. Okay. So what are these people going to do? Only some people can make the transition to the jobs that are new, replacing the old ones. And then you have the 18-wheeler drivers, the truckers, okay? Because those jobs will be going away too. Because it is expensive to hire someone and pay the insurance to drive those 18-wheelers around. If you can automate those things, they'll be automated. So
they
no
have
months
to retrain, right?
Huh?
They have to retrain to some other jobs, right?
But the number of jobs that is being displaced, or the net amount that is being displaced, is positive.
Right.
Which means you're getting rid of a larger amount of jobs while introducing a smaller number of jobs because of the replacement, because of the technology. So the question is, what are people going to do?
Retrain, right? That's what I'm saying. Try and do a different job.
Well, what kind of different jobs are we talking about? McDonald's is going to automate. Okay, it's just a matter of time. They already have automated, McDonald's at certain places already as experiments. So you can probably kind of think of it like 5-10 years in the future. Most fast food places will be at least semi-automatic. So what can people do when they are no longer getting jobs like that?
Riot.
Huh?
Riot.
Riot. You mean a game company?
Huh?
League of Legends?
Good old fashioned revolution.
Well, we don't know, because it is the same kind of problem when we mechanized farming. Okay, in the good old days, we don't have harvesters, so how do people harvest corn from a cornfield? They hire a lot of people. Okay, now that we have harvesters that are GPS based, that are fully autonomous, we don't need people in the farms anymore, or at least not in the field, right? So what did the government do so that we don't end up in so that those people don't end up being
They tax the machinery.
well, they got subsidies.
It's a term for subsidies.
They got subsidies. In other words, oh, you don't have to work anymore, and we'll send you money so that you can continue to live at the same standard of living. That is not true.
I mean, it could. It's not gonna. They're not gonna do that for all the people getting displaced, though.
Well, they have been trying to.
Well, what people think was, what people thought was, if you keep giving these people money, they will just stay at home and just, and their offsprings will stay at home, and then you will just have more and more people, using that as an income. But that turned out not to be true. A lot of younger people from those, farm towns, they went to the cities because they couldn't stand the boredom, just staying home. So the question now is, what kind of jobs will be in the future that people can still do that machines and automation and AI cannot do. So that's some question for you guys to kind of ponder upon when you have time, because I think we are walking into a future that definitely is heading in that direction. Okay. I'm older than you guys, so I'm kind of lucky. It's like, okay, you guys have to deal with it. I have less time that I have to deal with that.